If there are not questions, spending the time, I will go to the second presentation that comes from Japan, Professor Iwaki Akiyama, and the title of presentation will be Simultaneous multimodal imaging of ultrasound and MRI. Please.
Thank you, Chairman, and ladies and gentlemen. I'm from Japan, and I'd like to talk about the simultaneous ultrasound MRI multimodality imaging. I'd like to explain this kind of new technology. This study was supported by Japanese government. I completed this development in 2017. The purpose of the study is, I'd like to explain today's talk. Feasibility study for multimodality imaging of ultrasound and magnetic resonance. The main point is to develop ultrasound array probe applicable to high magnetic fields and magnetic resonance imaging. And second, estimation of sound velocity in vivo by MRI and ultrasound echoes. The third, the improvement image degradation in BIM scan image due to disagreement of sound velocity assumed in the system to that of actual tissues. Because the ultrasound pulse echo imaging is based on the uniform sound velocity distribution. If the different value of sound velocity existed in some area, the artifact occurs in the BCN image. So it is important to obtain the distribution of the sound velocity before the ultrasound imaging. If you take MRI, the correct spatial, distribution by using the MRI, so we can estimate the sound velocity by using the MRI from the spatial information and the ultrasonic echo, the time information. This is the actual imaging system of MRI and ultrasound. This is the MRI room, this is the operating room. So ultrasound imaging system is located in the operating room. So in this room, it is not so high magnetic fields. So we can use the commercially available system. But in the MRI room, usually a very high magnetic field. So it is important to develop the high magnetic field resistance probe like this. The probe is located here and the object here. This is the head cord, this is the head cord and the MRI gantry here. So in this case, it is important to suppress the electrical noise. So we use this double input, connector here. This is the wall dividing the MRI room and the operating room. So the probe is connected by this, connector, and also the ultrasound equipment is connected this, type of the connector. So we can ground line here, so we can suppress the electrical signal. So This is the, just I explained, the operating room and the MRI room, and the probe here, and also this is the probe which we developed. That you can see here the yellow cylinder. This is the MRI markers shown right here, like this. This MRI marker is located in two lines here. Between these two lines, we have the array transistor located here. So it is important to configure or specify the slice of ultrasound imaging area and corresponding to the MRI imaging. So it is important to use this kind of MRI markers. So the feature of the probe is manufactured to be used in high magnetic field of MRI, and the probe is attached with MRI markers to appear in MRI. So we can the location of the probe in the MRI imaging. There's method to match the slice of base scan images corresponding to the 2D plane in MRI is developed. So we developed two types of the probe. This is the low frequency, 5 MHz, and this is the 8 MHz. The frequency is different, and also the element pitch is different. This is 0.36, and this is 0.30. So also number of elements is 256, and this is 192. And also I'd like to add a comment on the acoustic lens. Well, it's not available, but this is the focal length of 20 millimeters. So it's the first developed this type of probe, and the second, developed the probe here. These two probes used in the high magnetic fields. So this is the ultrasound imaging system. This is not commercially available system. It's a special developed in this study. But the concept or the basic thing is the same as the commercial available system. The interface channel is the maximum value is 256. The channel is 128. The AD resolution 12 bits, and the sampling frequency is about 30 MHz. And the capacity of capture memory is 256 megabytes per channel. So first I'd like to show you about the estimation of the sound velocity. The sound velocity is calculated by division of length by time of flight. Spatial information is obtained by MRI. The time of flight is obtained by ultrasonic echoes. So experiments is applied to the muscle and fat tissue in cow. The MRI is Hitachi on Vega, 1.5 decimal. Here are the images of the MRI for the cow. This is T1 weighted image, this is T2 weighted image, and the diffusion weighted image. We have three types of image, and we have this is the T1, T2, D value is shown here. So we need to specify the ultrasound, the slice image here is corresponding to MRI. This cross-section is same part of curve. So we can obtain the spatial image information and the time of flight information, these two images. This is the estimated value of sound velocity. 8 MHz probe, this is the 5 MHz probe. The fat and muscle is the sound velocity. Is fat for this value and muscle here. So this is the standard deviation here. This is the results by using 5 MHz probe. The fat tissues a little bit lower than this probe. Also muscle is a little bit higher than this. So we can compare these two values, but we have this value is good, and also these values agreed with the literature value. So high frequency is much better than the lower frequency. The measurement accuracy is better than this. So next, I'd like to show you about the phantom experiments by using to compare the sound velocity distribution compensation. And this slide is a little bit different from the proceeding here. This is much better than this. So this image is sound velocity corrected, sound velocity estimation, and this is not used for the compensation. So if you take a look at this red area, so you can see the spatial resolution is better than this. So in this example, it is important to obtain the sound velocity distribution beforehand to imaging by ultrasound. And this is showing you on the results of the spatial resolution and the 3 square of the red, 3 area. We have the spatial resolution. It's better than 0.5, about 0.3 and 0.4. The average 0.4. So about the spatial resolution is better than the double in this experiment. So next, I will show you neck imaging by using this. So this is a probe, and here we can see the acoustic copper gel. This is used for to simulate the fat tissue, because this copper gel part, the sound velocity is nearly equal to the fat tissue, and also thickness is 10 millimeter. So this is the example. The MRI images of neck is the acoustic gel part. This white area is responding to the acoustic gel part. And you can see this image is showing you about MRI markers. So we have two lines of MRI markers. So this slice and this slice. The probe is located between two images. So we can obtain the slice, which is equal to the p-scan image by using these two images. This is the result, and I compare the results of the sound velocity compensation by using this technique. So if you take a look at this area, this is the thyroid, so you can compare these two areas, and this image is obtained by proposed method of compensation. This image, no compensation. I mean, this is the commercially available, system. So we calculate the resolution, lateral resolution, and the signal to noise ratio. So the improvement of lateral resolution is 0.6, and the signal to noise ratio improvement is 3 dB. So we have the compensation of the acoustic gel part of sound velocity is lead to this result. Next, in this case, we measure the sound velocity by using ultrasound MRI. But in the future, we can estimate the sound velocity MRI only. This is the case for the plan. So I'd like to explain the bovine fat. This is the bovine muscle. That we measure the sound velocity of these two tissues and compare the MRI. I mean the T1, T2, and the diffusion values measured by MRI. So this is the experimental system for measuring sound velocity. And also, this is the experimental system for measurement of T1, T2, and diffusion value. The sample is in the here. So all together like this, and put it into the MRI gantry like this. So if you take a look at these results, the horizontal value is the T1, and the vertical axis is the sound velocity. This figure is showing the horizontal axis T2 value, the vertical axis corresponding to the sound velocity. This is showing the diffusion coefficient of here, and the vertical axis is sound velocity. The red plot is fat, and the blue one is muscle. So you can see these is classified two areas. So we have these three approximation equation we have. So we can estimate by using the T1, T2, and diffusion value. From this expression, we have like this. So I'd like to conclude my presentation. I should explain the multimodality imaging system for US and MR was developed. The ultrasound for simultaneous imaging and MRI was prototype. As a result of experiment using 1.5 Tesla MRI and 8 MHz ultrasound probe, some velocity of muscle and fat tissues in cows were measured in vivo, and the improvement in image degradation of base scans was compensated by sound velocity dissipation was found. Thank you for attention.
Thank you. My question is, could you please share some clinical application of this technique or its potential in clinical practice?
We have not yet tried the clinical application. This is just basic, research. So in the future, we are trying to in clinical application for the various disease and for instance the cancer and also the liver, the kidney, anything.
You mean the fusion of the image, so we can see the exactly of the location in the MRI and ultrasound?
Yes. It is very easy to overlap two images. Mm-hmm. So we have some special information from MRI and ultrasound together.
So it's the same like in the MRI and FDG PET fusion?
Sorry?
I mean the technique is a fusion between two methods. Does it?
Yes.
Okay, thank you.
Cái kỹ thuật này thì nó hơi khác với cái fusion technique một chút, tức là kỹ thuật này là real time luôn, nằm ở trong cái máy cộng từ khác. Chúng ta đang xài cái fusion technique là hai room khác nhau. Ví dụ ở Hòa Hậu chúng tôi cũng làm cái siêu âm ở phòng riêng, rồi làm cộng hưởng từ trước, rồi sau đó làm để cái đầu dò vô trực tràng, mới dựa theo cái hình của MRI trước, rồi mình lách tới đó hai cái room khác nhau. Cái này technique là real time fusion. Thank you for your question.
Thank you.
We hope to future.
Yep.
We have the technology.
Yeah.
Yeah. 2 and 1.
Yeah.